There is actually, to that end though, there is one thing I feel like we didn't talk about when it comes to inverse trig, and there's a few, and just a couple of these problems on Professor Burke's homework. So I'll talk about these two things. So I do think they're worthwhile. Well, I mean, I think it's all worthwhile, but I saw these, I'm like, oh, these kind of seem kind of funky. So what if I wanted to evaluate, say, I don't know, something like tangent of arc cosine of 1/2. Terrible. Who wants to do that? This one's actually, so these ones in the REL thing are not so bad, because arc cosine of 1/2 is actually an angle we're kind of expected to know. Now here's the nice thing about this question. You don't need to know what arc cosine of 1/2 actually is. I know, because I've done this forever, the arc cosine of 1/2 is, actually, let me see. It's the angle whose cosine is 1/2, and the angle whose cosine is 1/2 is pi over 3. And then we can find tangent of pi over 3, which is square root of 3. But let me point out, I did that from memory, right? Like you might not remember those things. And the thing about this particular type of question, trig function of inverse trig function of value, is you can totally get away without knowing any trig functions of anything. Let me show you what I mean. Arc cosine of 1/2. I know it's an angle. Is an angle. Let's call it theta. And it's an angle such that cosine of theta is equal to 1/2. Do we know that angle? Sure. It's pi over 3. Do we need to know that? No, we don't. Check it out. Draw yourself a little triangle. And there's your angle theta. And cosine is which side over which side? SOHCAHTOA. That would be sine. Adjacent over. I never, whenever I say SOHCAHTOA, I'm always like, I really have to emphasize the ka, SOHCAHTOA, because its cosine is adjacent over hypotenuse. SOHCAHTOA. So the cosine of theta is going to be the adjacent over the hypotenuse. The adjacent to this side, the hypotenuse to that side, and we can find the missing side. So this side here, 1 squared plus question mark squared equals 2 squared. So question mark squared is going to be 4 minus 1. And our question mark is the square root of 3. And now I can totally find tangent of that angle. Tangent of that angle is tangent of the arc cosine of 1/2. But tangent of that angle is opposite over adjacent. So you can totally tackle a problem like this without knowing any trig values of anything. I don't need to know to do this problem that cosine of pi over 3 is 1/2 or that tangent of pi over 3 is root 3. I did it without that knowledge completely. It's kind of nice. In a similar way, I could ask you something like, what is, sure, I'm trying to make it interesting. I'm going to do 2. Let's say I want to find sine of inverse tangent of -1. Again, you totally could actually know what inverse tangent of -1 is. But I'm going to pretend like I don't. But I am going to know that inverse tangent of -1 is an angle. It's some angle. Inverse tangent of -1 equal to an angle is equivalent to tangent of that angle equals -1. I don't actually need to know that the angle is whatever it is. If tangent's equal to -1, the negative is an issue here. I'm going to ignore it. So ignore this negative for a second. And I'm just going to say tangent of theta is equal to +1, which is 1/1. I know I didn't draw this to scale. Clearly those sides should be the same length, but they're not. Let's find the hypotenuse. So 1 squared plus 1 squared equals h squared. So h squared is 2. So the hypotenuse is the square root of 2. Oh, great. So now if I want to find sine of this angle, it's going to be the opposite over the hypotenuse, which is going to be 1 over the square root of 2, which we typically rationalize as the square root of 2 over 2. But now I need to think about that negative that I was ignoring before. So inverse trig functions are kind of weird. Inverse trig functions, you get values that are in one of 2 different quadrants typically. For inverse sine and inverse tangent, the values you get are in quadrant 4 or quadrant 1. So the range of y equal to the inverse sine of x is negative pi over 2 to pi over 2. And the range of y equal to the inverse tangent of x is almost the same, except you don't get the ends. And the range of cosine, sorry, inverse cosine is unfortunately not the same. It's 0 to pi. Here's what that means. It means that this angle was in quadrant 4. And I'm taking sine of this angle. Well, in quadrant 4, is sine positive or negative? Definitely negative, right? Because all students take calculus, and cosine is positive in quadrant 4, so the other 2, sine and tangent, are negative in quadrant 4. So that's definitely going to be a negative root 2 over 2. On the other hand, I will also point out that cosine of the inverse tangent of -1 would be positive 1 over root 2, which is positive root 2 over 2. Because that angle is still in quadrant 4, and in quadrant 4, cosine is positive. In case anyone wants to know, the inverse tangent of -1 is what angle? So this is where people, so here's, I'm going to write a wrong answer first. Here's what it's not equal to. It's not equal to 7 pi over 4. That angle is in quadrant 4, and it is true, I should point out, it's very much true, the tangent of 7 pi over 4 is equal to -1. But inverse trig functions have a very, very specified range. So if I take inverse tangent of -1, I can't get any old angle I want, right? Because there's lots, literally infinitely many, of angles if you take tangent of the -1. But we want inverse tangent to be a function, meaning if you input something, you have to get one and only one output. And the output we have all agreed on for inverse tangent is going to be in quadrant 4, but kind of backwards. Right? We're going negative angles. We're going to get negative pi over 4. The nice thing about inverse tangent and inverse sine is if you know what inverse tangent or inverse sine of a positive number is, you know the corresponding negative value. So just as a quick kind of addendum here, if you know that the inverse sine of 1/2 is pi over 6, then you automatically know that the inverse sine of -1/2 is negative pi over 6. Kind of nice. It does not work for inverse cosine. The inverse cosine of 1/2 is pi over 3, which we already pointed out. The inverse cosine of -1/2 is 2 pi over 3. You have to be over in quadrant 2. Okay, but I don't want to spend, I didn't want to spend really any time talking about inverse trig functions, but it did seem like that was pertinent. But yes, definitely go back and look at the derivatives we did a while ago. They'll help you out. But let's go ahead and talk about, I already forgot what I said I was talking about. I'll remember in a second. Oh yeah, linearizations and stuff. So linearizations, you should feel good about them because you already know what they are. So linearizations, just a fancy word for the equation of the tangent line. That's kind of it. Oh, you may want to see the thing I'm trying to write down. That's a good idea. Yeah. Let me do this as well. Sorry. Get a little more space there. Let me grab my notes here. So how do you want to talk about this? There's a number of ways to talk about this. Usually people often kind of start with, does that say edge? It says equation. Equation, EQN, equation of tangent line. I know it's an abbreviation. So people kind of use linearization in a variety of ways. One of the main ways is by asking the question, use a linearization to approximate or estimate, and let's start off with something not too terrible, the square root of 51. Okay, there's a lot rolled up in this that we haven't really said. So people might, this is kind of the bare bones question that someone might ask, with giving you kind of nothing. Here's the same question, giving you more information. Use a linearization of f of x equal to the square root of x at a equal to 49 to estimate or approximate the square root of 51. They're telling you a little bit more information. The point I'm trying to make here is that if someone told you or asked you this, we should be able to look at this and kind of see what the function is and what the a value is without too much effort. A little bit of effort, but not too much. So if I'm looking at this version written in black, here's what I want to know. I want to know what f of x is and what a is. Why do I even want to know that? Right? Like, what am I doing with this? Well, here's the idea. So f of x is going to be, the way I think about it is if you're trying to approximate the square root of 51, whatever number is being plugged into the function, in this case 51, replace that with x. That's how you get the function that you're trying to use. There are lots of other functions you could use. You could say something like the square root of 2x plus 1, the square root of 3x minus 7, right? You can literally put anything in there and then try and find the appropriate x value, but why make more work for yourself? Right? The square root of x is going to be the easiest thing to deal with. And then, well, in fact, before we get too involved with this, here's what we're doing. I'm taking my square root function. And let's see if we can zoom in a little bit here. So here's my square root function. And the idea is I'm trying to use this function to estimate the square root of, well, I'm trying to use the linearization of this function to estimate the square root of 51. So I don't know what the square root of 51 is. I know what the square root of 49 is. Square root of 49 is 7, right? It's easy to plug in. So what I'm going to do is I'm going to plug in 49. And then when I plug in 49, I get a y value of 7. And then we're going to find the tangent line at that point. And then what I'm going to do is I'm going to plug in 51. And instead of plugging in 51 to the function and getting out whatever the square root of 51 is, which I don't know, I'm going to plug in 51 to a much easier thing. I'm going to plug in 51 to this straight line equation, which is going to be not terrible. And I'm going to get out an approximation. This line we typically call the linearization, right? Because you're literally just taking this function and trying to make it look linear around here. And I'm going to get the linearization evaluated at 51. And I want to make it kind of, I want to emphasize the fact here that this value here is really, really close to what you would get if you actually plug 51 into the original function. I will also mention that as you move further away from 49, your error is going to get bigger and bigger and bigger. Right? So for values that are close to 49, this is a good approximation of the square root of those values. But if you're trying to plug in something much larger than 49, this would not be very good because right, you can, hopefully you guys can see, right, this function is going to continue this way, and this function is going to continue this way, and they're going to move further and further apart from each other in either direction. Okay, so all we're trying to do is first find this linearization, meaning I want to find a couple things. I want to find, well, in fact, let's actually write out the equation. I know the equation of a line. It's y minus y1 equals the slope times x minus x1. I'm just going to, oh, sorry, thank you, good call. I'm just going to rewrite this equation of the line in a slightly different way. Really just using different names for things. I'm going to isolate y and write it as y equal to y1 plus m times x minus x1. And then instead of writing y1, I'm going to write f of a. Because what I'm really doing here is I'm saying this is my a value, and this coordinate here is a comma f of a. So if I'm finding the equation of the tangent line at this point, it's y minus my y value plus the slope. Well, the slope is just the derivative evaluated at that point. So the slope here is just f prime of a. And the x coordinate that we're plugging in is what we're calling the a value. So we typically rewrite this as the linearization instead of y equals f of a plus f prime of a times x minus a. But I want to stress it's literally just the equation of the tangent line where you solve for y. So in this particular example, our a value is definitely 49. Right? It's the closest number to 51 that's easy to evaluate in the square root. And then I want also my derivative because I'm going to need it. So prime of x, the derivative of x to the 1/2 is 1/2 x to the minus 1/2, or if you prefer, 1 over 2 times the square root of x. And I've probably run out of room here, so let's go ahead and page. And then I'm going to actually plug in my a value and find all the things I need for this. So f of a is going to be the square root of 49, which is 7. F prime of a is going to be 1 over 2 times the square root of 49, which is 1 over 2 times 7. And then I'm going to just throw everything at this formula. So now my linearization, my equation of my tangent line is f of a plus f prime of a times x minus a, and a was 49. And I want to kind of show you, or I want you to see that, right, if you pick a value of x close to 49, this part here is going to be small, which makes sense, right? Because if I'm plugging in 51, the square root of 51 should just be not that much different than the square root of 49. Right? They're pretty close to each other. They're going to be pretty close to each other. So let's see what we get here. So I'm going to approximate the square root of 51 with the linearization at 51. All right, square root of 51 is what you get when you plug it into the actual black function here, and L of 51 is what you get when you plug it into the red line here. They're pretty close to each other. Let's see what we get. This is going to be 7 plus 1/14 times 51 minus 49, which is going to be 7 plus 2/14, which is 7 plus 1/7. And at least on some people's web work, you actually have to do the simplification here. You need to either write this, I think they would take a mixed fraction, so you can write a 7 and 1/7, which is terrible, or the more normal way of writing it, which is an improper fraction, where you say, oh, this is going to be 49/7 plus 1/7, which is 50/7. Neither of these is really nice to kind of compare it to the actual square root you get with the calculator. So if I was going to actually figure this out, I know that this is approximately 7.1428, etc. Whereas if you use a calculator, I should have done ahead of time, but I didn't. So we use a calculator, calculate the square root of 51. What do we get? I hate that when you, so I don't know if you guys ever run this problem. You open your phone, but you just open the calculator part and then you try and turn it to the side, but it doesn't do it because you actually haven't opened your phone. It doesn't want to give, it's like, oh my gosh, come on. Give me the whole calculator. Why would you be so difficult? And now I can do it. Thank you. Okay, 51 square root. It's about 7.1414. Calculator. So pretty good estimate. A couple things I want to point out with this linearization idea. One thing to be aware of is you don't want to simplify this. Meaning it is not in your interest to say that L of X is 7 plus 1/14 times X minus 49 over 14, and then to put those together. That's going to end up being 1/14 X. 7 is 98 over 14, and 98 minus 49 is 49 over 14. But plugging it, right, it's usually just, it's not going to make your life easier. Don't do this. The whole idea, we're looking for Co-21A?
Yes.
Come on in.
Oh.
I didn't see your symptom survey though.
Oh, okay.
The whole idea here is that when you calculate this, this part here is going to be small, and so it's going to be easy to do this calculation. Let's see another example. We'll do two more estimating examples, and then we'll kind of move on to what's. So,
Here you go. Thank you so much. Appreciate it. Have a seat.
So we want to estimate 1.98 to the 5th power. So how are we going to do this? Well, we need to identify the three, two things really, but three, I like to say 3 things. So we need to figure out what our function is, and then the derivative, but once we know the function, find the derivative. And then we also need to find the nice A value we're going to plug in. So what makes sense to use as a function here? Well, again, I'm just going to take my expression and replace the number with a variable x. I'm going to say my function is going to be x to the 5th. And we can, obviously, the derivative is 5x to the 4th. All right, let me ask you all, what's a number that's close to 1.98 that's easy to plug into this function?
2.
Right, 2. 2 is the staring us in the face answer to that question. Usually they're going to try and make it pretty obvious what you should actually be. All right, so then we have our linear, I guess I should figure out. So f of a is going to be 2 to the 5th, which is 32. And f prime of a is going to be what? 5 times 2 to the 4th, which is 5 times 16, which is 80. Okay. So now if we write our linearization, again, it's just the same formula as every other time. It's f of a plus f prime of a times x minus a. And then if we actually plug in our values, we're going to get f of a, which is 32 plus 80 times x minus 2. All right. Again, I want to mention here that you do not want to simplify this any further. I'm going to be plugging in 1.98 because I'm going to say, okay, well, 1.98 to the 5th power is approximately my linearization at 1.98. And I'm going to get this, which isn't going to be too terrible. But I do want you to see that if you simplify this, said it was 32 plus 80x minus 160, and then 32 minus 160 is what, negative 128. This might feel like it's simplified and great, but plugging in 1.98 here feels dumb. Right? If I plug in 1.98 here, 1.98 times 80 is more calculation than I want to do with my brain, more calculation than I need to do, right? Because if I plug in 1.98 here, it's a lot easier. Because I'm going to do negative 0.02 times 80, which I think is just an easier calculation. So don't simplify this linearization. It's not in your best interest. This is going to equaling 32 plus 80 times, oh, actually, so I made a kind of error here. I didn't actually plug in the 1.98 for x. I should have written this as 32 plus 80 times 1.98 minus 2, which is then 32 plus 80 times negative 0.02. It's going to be 32 plus, let's see, 8 times 0.02 would be 0.16. So it's going to be a minus 1.6, I think. That seems right. Which is going to be 30.4. It's not necessary, but I do like to compare it to what the actual value would have been if we plugged it into a calculator. So if we take 1.98, usual problem, we plug it into a calculator, we get approximately 30.4317. So pretty close, right? That's kind of the idea. Let's look at a couple. Yeah. So this is kind of one variety of question like this, where like estimate this thing using no linearization. Yeah, we should do, there's one or two more I want to show you just because there's a couple strange things that can happen. So let me show you one more specifically, and then we'll look at some other varieties. I want to estimate, sure, tangent of 46 degrees using a linearization. All right, same process as before. We want to identify all the things. So my function of x is going to be tangent of x. And my a value, what's close to 46 degrees that's easy to take tangent of?
45.
Right, exactly. Again, we're trying to make it easy to see what the angle is supposed to be, or whatever the value is supposed to be. And then we also need the derivative. The derivative of tangent of x is secant squared of x. And then we're going to plug it in. So f of a is tangent of 45 degrees, which is 1. And f prime of a is secant squared of 45 degrees. I never remember secant of anything. I know that secant squared is 1 over cosine squared. And I know that cosine of 45 is root 2 over 2. So that's going to be 1 over root 2 over 2 squared. That's going to be 1 over 2/4, which is going to be 4/2, which is 2. Okay. So now we're going to write our equation. Now, I'm going to warn you, I'm going to make a mistake. That's kind of the point of this problem. Is there's a mistake that's easy to make that is we need to correct. So here's my equation. It's f of a plus f prime of a times x minus a. And my f of a is going to be 1. My f prime of a is 2. And my x minus a is x minus 45. Okay. So here it comes. Well, actually, I've already actually made the mistake, but now it's going to amplify and we're going to see how it's a mistake. So I'm going to try and approximate tangent of 46 degrees, approximate the linearization of 46, which is going to be 1 plus 2 times, I should have done 44. Oh, well, such is life. 46 minus 45, which is 1 plus 2 times 1, which is 3. Which seems kind of wrong. Because tangent of 45 degrees was 1. And we went 1 degree bigger and tangent jumped up to 3. I will also point out, because another example that we typically do is actually do tangent of 44 degrees. If it's tangent of 44 degrees, it would be that, which is 1 plus 2 times 44 minus 45, which is 1 minus 2, which is -1, which seems extra wrong because 44 degrees is in the first quadrant, and tangent should definitely be positive in the first quadrant. So what's going on here?
We didn't convert from degrees to radians.
Right, exactly. So the thing we need to be aware of is that this is actually degrees, this is degrees, this is degrees, this is degrees, this is degrees. Now, here's what I would encourage you to do. You don't want to convert to degrees right now. 46 degrees is a terrible number in radians. 44 degrees is a terrible number in radians. So is 1 degree, but we have to deal with it at some point. But what you want to do is kind of work this as much as you can until you have to convert. So this is actually going to be 1 plus 2 times 1 degree, which is 1 plus 2 degrees. If it doesn't say degrees, you automatically assume it's in radians. So this 1 here is 1 radian, which I know seems kind of weird, but it is. Am I saying the right word here? I feel like I'm saying something kind of funky here. Let me make sure. No, I mean, yeah, it's in radians because radians are the unit that doesn't have dimension. So the assumption is if it's not degrees, it's in radians. And so what we're going to do is we're going to convert this radian to degrees. Not 2 as in the number, but 2 as in from this to that. So this is going to equal 1 plus 2 times pi over 180. And that's going to end up being 1 plus pi over 90. And I would leave it like that, but you could also write it as 90 plus pi all over 90. And that seems like a much more reasonable answer for what tangent of 46 should be, 46 degrees should be, because it's a number that's pretty close to 1. And that should kind of always be the case when you're doing these linearizations. Right? If you're trying to estimate tangent of 46 degrees, it should be pretty close to tangent of 45 degrees. Or if you're trying to estimate the square root of 102, it should be pretty close to 10 because it's pretty close to the square root of 100. So whenever you're doing these linearizations where you're estimating stuff, that's kind of the whole point, is your value should be close to whatever the easy value is to get. All right, let's shift gears just a little bit. Sorry, I got lost after 1 sec. Yeah. Okay. Sure. I'm trying to keep things in order here. So let's look at this example. How much does f of x equal to x squared change if x goes from, say, 5 to 5.2? Oops, sorry. And we're going to actually calculate this, and then we're going to approximate it. So let's draw a picture. Well, here's f of x equal to x squared. Say here's 5.2. So this amount here, all right, if I plug in 5 to x squared, I get 25. If I plug in 5.2, I didn't calculate this ahead of time because, again, you know, that's the way I do it. 5.2. 27.04, which I suppose we could have done by hand, but come on, we're going to use the calculator. So the actual change, exact change, is going to be delta f. My nose really itchy. Sorry, 1 second. Itchy nose. Okay. Delta f is f of 5.2 minus f of 5, which is going to be 27.04 minus 25. Which is exactly 2.04. But the whole idea with these linearizations is that we can estimate the change. So what we're also going to do to estimate the change is, again, every time, right? It's always the same thing. You're looking at the tangent line. That's my tangent line. And what we're going to say is, okay, instead of calculating this, which is delta F, we're going to calculate this, which we typically call dF, the differential. Here's why we call it that. So, approximate change so dF, well, if you look at this tangent line I've drawn here, to find dF, I'm really just trying to find kind of, I'm going to call it the rise, right? If you think about the slope being the rise over the run. Well, I could actually really call that then the rise over the run times the run. Or as I would like to say, it's the slope times the change in x. Because the run is how much x you've got, change. Or more specifically, the derivative times the change in x. Right, the slope of the tangent line is the derivative at the point. So I'm trying to find how much rise I've got here. It's just going to be exactly what we think it is. It's the derivative, the slope of the tangent line, right? So actually, let's find it before I keep talking here. So my derivative here is going to be 2x. And if I plug in 5, it's going to be 2 times 5, which is 10. So this is that telling me on this line, every time I move over 1, I move up 10. I want to know how much up I'm going to move when I move over 0.2. Well, if I move over 0.2, I'm going to move up. Well, it's actually, we use calculator, right? If I move over 0.2, 0.2 times 10 is going to be 2. Right? For every 1 unit I move over, I move 10 units up. So if I move 0.2 units over, I'm going to move 0.2 times 10 units up. So my dF is exactly my derivative, which you can write as dF dx, or you could say it's your f prime of a times your delta x, which is 10 times 0.2, which is 2. Notice those are pretty much the same. They're not exactly the same, but they're very close to each other. What I should say about this is in your linearization formula, this is like the second half of it, meaning, sorry, I know this is really super itchy. It's kind of killing me. Right? If we were finding the linearization here, which would be f of a plus f prime of a times x minus a, this part right here, that's your df, your differential, the part that is approximating the change in f. So if I instead ask the question, what is, I want to approximate 5.2 squared using a linearization, we've already done the work. All we're doing is we're saying, okay, well, 5.2 squared is going to be approximately 25 plus this change here. So 5.2 squared is approximately 5 squared plus your df. Oh man, I don't know why. It's like just, my nose is the itchiest it's ever been. I know it's not your problem, but it's my problem, and you guys get to see it. Okay, sorry. Okay. So what we're saying here, right? This is really just, this is my f of a plus my f prime of a times x minus a. But I really, really, really want to make it clear that this part here is kind of the approximate difference between your actual value and your desired value. Yeah.
So what's the difference between taking the derivative of that and then seeing the change in that. What's the difference?
So that's a good question. So the change in f is kind of like just the top part of the derivative. Now I know, so when people write df dx, well, depending on your teacher, when someone writes this, they should make it clear it's technically not a fraction. I know it looks like a fraction. We treat it like a fraction. It has a lot of fractional properties, but it's technically not a fraction. It's notation that indicates we're asking how f is changing as x is changing. So this is the rate of change of f as x increases. That's what that notation actually means. But in every way, shape, and form, we can treat this like a fraction. It acts like a fraction in every way we need it to. So this is the derivative, whereas the change in f is that, which is approximately that, just the top part, just the, what we call the differential. Well, because they're not equal to each other. So if we go back to this picture here, so this, you're asking a really good question. So the actual change in f from here to here is that difference from there to there. It's f of 5, I should say really, it's f of 5.2 minus f of 5. And that is the actual change in the function value. But the differential is an approximation of that. It's literally just, I mean, you should really, when someone says the differential, you should really think of, oh, it's the rise. Right? If you're thinking about the slope, or I should say, if you're thinking about the derivative being the slope of the tangent line, then the differential df is the rise part of that slope. So if you know what the run is, then you can say the rise over the run is equal to the slope. So, yeah.
Sorry, one last thing.
Yeah, no, you ask all the questions.
So I assume that we can only do this for very small approximations, because I assume that.
Right. So like if this delta x gets really, really large, it's not that you can't do it, it's just that your approximation no longer is very good. But yeah, so it's totally the case that, sorry. So when we're talking about this, what we're saying is the derivative is an approximation of the actual change in f over the actual change in x.
We can't see the bottom.
Oh, sorry, thanks. Which is your rise over your run. And so if you're trying to approximate delta f with your df, sorry, it's going to be equal to, well, df is your derivative times your run. Right, again, this is the rise. This is the slope. This is the run. And we know rise over run equals slope, so rise equals slope times run. Yeah.
So it's because they kind of cancel out, even though it's not a fraction, it has fractional properties.
Yes, exactly. They kind of cancel out, but we don't actually really cancel them out. So yeah, like it would be, it's not that we couldn't cancel these out here, like we could and just get back to df, but the thing is, we're trying to find this by using this and this. So we can find the derivative, we can find the run, and then we can multiply those things together to approximate, to get the rise. And the rise is an approximation of the actual change. And again, I would keep this picture in mind, right? This is your approximate or your approximation of this actual difference here.
So it's a little noticeable, but it's still a good approximation.
Right. Yeah, it's definitely an approximation. But the point is, and now certainly for this example, it's not hard to actually calculate 5.2 squared. Right? You can do that by hand if you have to, or with the calculator very easily. But the idea here is that this can be used to approximate things which are more of a pain to actually calculate. let's look at some examples. And again, I'll say this here. So let's say we have a sphere with a radius of 3 inches is coated with ice that is 1/4 of an inch thick. What's the approximate volume of ice? So I'm not actually trying to calculate the entire volume of the new bigger sphere. I'm trying to approximate just the difference in volume between the sphere and the sphere with ice. So here's my original sphere. It's got a radius of 3 inches. Yeah. And I know the volume of this, or I know how to calculate the volume. The volume of this sphere is 4/3 pi times the radius cubed, which comes out to just be 36 pi. And my slightly bigger, okay, now we're going to coat it with ice. So it's going to be my old sphere inside. There's my bigger sphere with ice around it. This bigger sphere has a radius of 3¼ inches. And the volume of this would be 4/3 times pi times 3.25 cubed, which seems terrible. I don't want to calculate 3.25 cubed, at least not without a calculator. But again, that's not the point, right? We're not actually trying to calculate the change in volume, which would be the volume evaluated at 3¼ minus the volume evaluated at 3. We're trying to approximate that. So we're going to find dV, the differential. And again, we're always thinking about calculating this as the derivative times the change in the independent variable. So instead of saying, right, so again, you should be thinking of V as like the Y, or as like your output, essentially, right? Your thing that's going to rise. And I want to find this is going to be the slope times, yeah. And I'm just trying to think, I'm like, yeah, there's just a way you can either think of it as dr or delta r. The thing is that, so here's the thing that people often have like a little bit of a sketchy time with. Delta V is being approximated by dV, but delta R and dr are the same. I know, right? It seems kind of wrong, but we're thinking about dr as just the change in r, and it can kind of be whatever you want it to be. So we're letting, right, if you go back to this picture I had before, right, in this picture, I'm calculating delta F over delta R as this change over this change, or I should say delta F over delta X, and dF over dx as this change over this change, but the dx and the delta X are kind of the same. I don't want you to get too hung up on it because it's not that big a deal, but what we typically do is we call this and that's the approximate.
So the change in R is our input, right? Like how much our input changes.
Exactly. Yeah.
And I assume it would change by 0.25.
Correct.
To get the difference.
Yep.
Derivative of the formula?
Yeah, exactly. That's what we're going to do. Yeah, well, I just had, so often people, so I kind of think about it this way because that's just where I've always kind of started with. I'm like, I'm trying to find the change in V, but you could also work it this way if you really want to. You can say, I'm going to start with just the formula. V is 4/3 pi r cubed. The derivative, dV dr is 4 pi r squared. Fun fact, that's the equation for the surface area of a sphere. In fact, it's kind of interesting. This is just a quick aside here. This is only true for spheres and circles, but like the derivative of their larger quantity equation is equal to the next thing, meaning the area of a circle is pi r squared, and the derivative is what? Which is the what of the circle? the circumference. And the volume of a sphere is 4/3 pi r cubed, and the derivative of that is 4 pi r squared, which is the surface area. It's not true for other shapes, but it is interestingly true for circles and spheres. There's probably a good reason for that. Like it probably has to do with the fact that a sphere and a circle a sphere you get the most volume for the amount of surface area you're using, and a circle you get the most area for the amount of circumference you're using. It probably has to do with that, but I don't actually know why. So now that we've got this, we're just gonna, oh yeah, go ahead.
Sorry, what happened to the, oh no, never mind. I forgot the threes cancel out. I was gonna ask what happened to one.
Yeah, threes cancel. So I will point out that we do, and again, right, I'm gonna quote unquote, I'm not really, but I'm gonna essentially multiply both sides by dr and say that dv is equal to 4 pi r squared times dr.
What makes this equation different from the others we were doing before? This seems a little different.
Then the linearization equation. So we're just, in this part, we're really just finding, well, in fact, let's do this and then we'll do a similar question with the linearization and we'll talk about how they're different. So I should point out though that this is the differential. The reason I point that out is because sometimes they're going to ask you to find the differential. And literally, like I know I'm looking at some of these homework equations where they ask you to find like dy or d whatever your function name is. The differential is literally just take the derivative and multiply it by d whatever your independent variable is. So if I was trying to find the differential, it'd be the derivative times dr. That's all the differential is. It's your derivative times d whatever your independent variable is. In this particular example, we're trying to actually use this to approximate delta v. And now we're just going to plug in the values. So we're going to plug in 3 for r. Why not 3.25? Because 3 is the easier number. It's the only really good answer to that question. And then your dr value, which was your radius is changing by 1/4 of an inch. Excuse me, I think it's a little bit. Notice that the units work out. I didn't write them in there, but that's a 3 inches squared, and that's 1/4 of an inch. So I end up getting inches times inches times inches, which is cubic inches, and that's a change in volume. So it does make sense. So we're going to get that this is equal to 4 times 1/4 cancels out, and you get 9 pi. If you want to use a calculator, that's about 30.7 cubic inches. Oh, sorry, that's not that. That's the actual calculation. Apologies. That's about 28.3 cubic inches. If you actually calculate this change here, it's going to be about 30.7. So if this sphere, if this sphere has its radius increased by 1/4 of an inch, the volume approximately increases by 28.3 cubic inches. Okay, but let's totally revisit this problem and talk about it from the linearization point of view. So here's what I'm going to say for the next part. We're going to use a linearization to approximate the volume of a sphere with a radius of 3 1/4 inches. Okay, so we need to identify our function and our input and our a value of the group. So our function, I'm going to write it in the normal way, meaning I'm going to write my function as v of r. Right? Volume as a function of radius. We know the volume of a sphere. It's 4/3 pi r cubed. And what is the nice a value we're going to use instead of 3.25? Yeah. And our derivative, of course, is 4 pi r squared. I'm also going to find my f of a, which is my v of a, right? Which is going to be, just plug in 3 and you get 4/3 pi times 27. which is 36 pi. And my f prime of a, which is your v prime of a, which is your v prime of 3, is going to be 4 times pi times 3 squared, which is also going to be 36 pi. Somewhat coincidental that they're the same, right? They're not always the same. I feel like I made, let me double check. I'm not making a dumb mistake. No, I'm really not. They happen to be the same because we picked 3. So now we're going to write our linearization. L of r, right, so x is going to be f of a plus f prime of a times r minus a, which is going to be, so here's f of a, it's 36 pi. Here's f prime of a, which happens to be the same, times r minus my a value, which is 3. Okay. So when we calculate this, we get that the volume at 3 1/4 inches is approximately the linearization at 3 1/4 inches, which is going to be 36 pi plus 36 pi times 3.25 minus 3, which is 36 pi plus 36 times 1/4 is 9. So 9 pi. So here's what we've got. This part here is the volume of the sphere with a radius of 3 inches. And this part here is the approximate increase in volume when we go from 3 to 3.25 inches in radius. So that's the whole kind of, not the whole idea, but that's the idea here, is that this part here, this is what we calculated in the previous problem. In the previous problem, we were asked to approximate the volume of ice, aka to approximate the change in volume when you go from a sphere of 3 inches to a sphere of 3 1/4 inches. And when we calculated that, we got the 9 pi. And in this other one, we're being asked to approximate the total volume of the new sphere, which is the volume of the old sphere, right? This sphere here has a volume of 36 pi cubic inches, and we're adding on the approximate volume by the ice, which is the 9 pi here, which is what we're exactly getting right there. And we're getting 36 pi plus 9 pi, which is not the exact volume, it's the approximate volume.
So essentially for linearization, we're looking at the total change, right?
Well, I would say that the total change here is the 9 pi. The 9 pi is how much it changed. And if, really, it's just, we can ask different questions. You can either ask, what's the value you get when you plug in this new value, and how do we approximate that? Or you can ask, how much change is there from kind of what the previous easy value would have been to this new less easy value? And the differential is whether you're taking just the difference or taking the difference and adding it on to what you get when you plug in the easy value to the original function. Other questions? Okay, let's take a quick break so I can pee and get some more water. And you're all welcome to use the restroom, get water as well. I'll be back in like 3 minutes, probably ish. Or you'll, I'll be back shortly. Think about what questions you want.
I'm kind of new here. I didn't even know that there was a full class till like 2 weeks ago.
Are you struggling with that? What's
No lessons. That's great. Like, didn't you miss the way down?
I had.
I'm not 21. Oh, you're still 20. No, I'm 21. I'm still in the last seat. I should have. There's a way in it, like I'm not sure I should still attend because like This is very different than what I was expecting, I guess.
But when you do take this, you'll feel more confident because you have already been introduced to it.
What do you think?
Hmm?
What do you learn?
Optimization.
That's in chapter 4.
No, we were just learning that right now.
That's not bad.
I'll probably ask him about like he seems like a good guy.
Yeah.
Are you guys in physics? Yeah. Do you guys know the exact sections that are in the picture? Is it just all chapter 3 or is it also chapter 4?
I'll be
Yeah,
back. I
we
need to
can
go
get
get some
to
food.
that. Sorry? I think all chapter 4. Yeah. But we just took that. Yeah.
Yeah, go ahead.
So this is the graph, and it says that.
Oh, yeah. Mhm. Right.
But I'm not sure how to find them.
So when we're doing a linearization, A is the value that we're approximating the function at. So where so the linearization of a function at A, the A is where the function and the tangent line touch. Where the tangent line is. So
So we had 3.
yeah, exactly.
Okay, I see. Thank you.
Oh,
So I just signed up for this class.
Great.
I was the one that sent you the email.
sure.
And I have known Sarah and she recommended this class for me, but I'm not sure because I'm with Mulassi's and I think his
So this class definitely, you'll certainly learn interesting things in this class, optimization, but this class definitely does not kind of coincide with it. Because he is so different from all the other 21A classes.
I wasn't aware about that.
Sure, I mean, so you're obviously welcome to stay, you're also not required to stay. So we'll do whatever you want.
And because honestly, for me, I'm kind of stuck on these concatenating problem
Uh-huh.
because they're asking like very complex like
Right.
parts.
And while-
I know you're on linearization.
Right, and I'm about to start talking about graphical stuff, but we're probably not gonna get back to that.
Okay, then I'll probably have to head out there.
Okay.
Unfortunately.
No worries at all. I totally understand. Like, you want to make the best use of your time, and currently this is not it. I get it. You're always welcome. Please feel free to come anytime. We will certainly talk about graphing stuff next week. I think we're about to talk about absolute max and mins, finding critical points. That's
Yes, that's because for some reason, I don't know, he's doing these a little differently because we're learning about concavity now, but we haven't learned about linearization yet. I have an idea of it now, but I don't.
Right. Yeah. The hard part with his class specifically is just does things in such a different order than every other 21A class. So it's hard to kind of be talking about what he is talking about when he is covering it because everyone else is doing other stuff. Yeah. So I think And certainly, yeah, yes, we can definitely talk about some examples of our functions increasing, decreasing, local extrema. Yeah, so let's move along from linearizations, great as they are, we can be done with them. And let's talk about all the stuff you need to graph a thing, because that's really where all this is going. So when you talk about extreme values, local extrema, concavity, increasing, decreasing, all that stuff, you're really talking about all the pieces of information you need to graph something by.
Do you recommend I stay or?
I don't think we're going to get to talk about concavity today. And if that's specifically what you're looking for, we're probably not going to get there. We're going to talk about finding critical values though. So which is useful. It's really, yeah, you're welcome to go, no hard feelings at all. You're welcome anytime.
Thank you.
So let's talk about the extreme value theorem. Which really just says, if you have a function that's continuous on a closed interval, then it's going to have an absolute max and absolute min. So if f is continuous on the closed interval a, b, then f attains an absolute maximum and an absolute minimum, which occur at either critical points or endpoints. And the critical point is where the derivative is 0 or undefined. We'll get a little bit more specific with that in a little bit. Let's look at some examples. So let's look at this function here. Let's look at f of x equal to x cubed minus 6x squared on the interval from -1 to 7. Graphically, this looks kind of like, well, in fact, we can actually do a better job here. We factor out an x squared. Here is a very rough sketch of this graph. It's going to have an intercept at 0 and at 6. It's going to look kind of like this. I'm only drawing the parts of it that I have, right? I'm starting at -1. I'm ending at 7. And this graph definitely has to have an absolute maximum somewhere. The way I've drawn it, it looks like it's happening at 7, but I don't actually know that. And it has to have an absolute minimum somewhere, which is probably either going to be over here at -1 or somewhere between 0 and 6, wherever this critical value is right here. So our method or process for finding where the absolute extrema are to find the critical values at the endpoints and then plug them back into the original function to see which of those gives us the largest value and which of those gives us the smallest value. So finding the critical points is not too terrible. We take the derivative, just 3x squared minus 12x, and we set it equal to 0. Well, technically we see where it's either 0 or undefined, but we can all see that this function is never undefined, so we're not going to worry about that. I'm going to factor out a 3x. I'm left with x minus 4. So my critical values are going to be x equal to 0 and x equal to 4. So now I'm going to take my critical values and my endpoints and then plug each of those into the original function. I'm not using the number line. I'm not seeing where it's increasing or decreasing, right? Because I'm not talking about relative or local extrema. I'm talking about absolute. I just want to know what thing is the biggest, okay, which has the biggest function value, and what thing is the smallest. So I'm going to look at f of -1, f of 0, f of 4, and f of 7. So plugging in -1, I will point out it's usually much easier to plug things into the factored version here. -1's easy kind of either way, but if I plug it in here, I'm going to get -1 squared times -1 minus 6. Which is -7.
Plugging in 0, I'm going to get 0. Plugging in 4. 4 is where you kind of see it's better to do it this way. Because 4 cubed minus 6 times 4 squared is more mental energy than I want to spend. 4 squared times 4 minus 6 is a little bit easier, I think. That's going to be 16 times negative 2, which is negative 32. And then f of 7, again, right, 7 cubed, I definitely don't want to do. 7 squared times 7 minus 6 is much easier. 7 squared times 7 minus 6, which is just 49. And then we just get to ask, okay, which one's the biggest? Well, 49. That's the biggest. Which one's the smallest? Negative 32. All right, some language about how we talk about these things. You could say that we have an absolute maximum at x equal to 7 with a value of 49. So the maximum value is the y value. It occurs at the x value. And that's a broad, like, it's not just true for absolute maximum. For any kind of point you're finding for a function, the thing you're finding occurs at the x point with a value of the y value. So if I'm trying to find an absolute maximum, it occurs at x equals 7 with a value of 49. And I would say that this function on this interval has a maximum value of 49. And this function has a minimum value of negative 32 on this interval. And it occurs at x equal to 4. So we have an absolute minimum value of negative 32 at x equal to 4. Right. You could also say we have a maximum, an absolute maximum at the point 7, 49. You have an absolute minimum at the point 4, negative 32. That's probably the safest way to say it, because you kind of just like, here's everything I've got. Just be careful, because sometimes they might ask you for the maximum value. So like if I said, what's the maximum value of this function? Our answer shouldn't be 7, or their answer should be 49. They might also, but they might ask, where does the absolute maximum occur? And then our answer is 7, not 49. So just be careful. The where is the x thing. The value is the function value, or the y. Okay. Let's look at a couple more examples. So, yeah, let's look at this one. Let's find, again, so same question, absolute extrema of f of x equal to x over x squared plus 1 on the interval from 0 to 2. Okay. So again, we know we're going to use 0 and 2, and we're also going to find the derivatives, the critical points. So I'm going to take my derivative, all right, quotient rule, bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the denominator squared. And now we are in kind of the situation where we really do need to simplify these things, because we're trying to solve it set equal to 0. And somebody asked, what if they did not give you an interval to check for first? So if they don't give you an interval, they're probably not asking about absolute extrema. Not that you can talk about the absolute extrema of a function on the entire real number line, but typically if they're saying something about just a function, they're usually asking you to find the relative or local max and mins, which we're hopefully going to get to today. But that's definitely almost always, if you're talking about absolute extrema, it is on a closed interval. Which, okay, just as technically the entire real number line is a closed interval, but we don't want to get into that. It's not a big deal. So I'm simplifying this. You get x squared plus 1 minus 2x squared all over x squared plus 1 squared. Simplifying the top further, I get x squared minus 2x squared, so I get a 1 minus x squared over x squared plus 1 squared. I think it's worth factoring this equal to 1 minus x times 1 plus x over x squared plus 1 squared. And I want to see where this is either 0 or undefined. What's going to make it equal to 0? X could be either right, plus or minus 1. What's going to make it undefined? Nothing. It's never undefined. So worth checking for because we had a fraction, but the denominator is never 0, so we're safe. I mean, it's okay if the denominator is 0, just it isn't in this particular example. So these are my critical values. And now we're going to check the function evaluated at 0, evaluated at 2, evaluated at 1, and not at -1. Because -1 is not in our interval. Right? We're only here, we want to see what are the absolute extreme values of this function between 0 and 2. -1 is not between 0 and 2, so it's automatically excluded. We don't care about it. Often when people ask questions like this on an exam, they try to make it so there's one value that isn't in the interval, and you just pretend that one's not there. Forget about it. It's not important. At least if I was writing a test question, I would write it so that there was one that wasn't in the interval. So then we're going to plug these into the original function. F of 0 is going to be 0. F of 2 is going to be 2 over 4 plus 1. And f of 1 is going to be 1 over 1 plus 1. So we have an absolute minimum at x equals 0. So a minimum at x equals 0. Or really, if you want, let me say it the smart way. Let's say we have a minimum at 0, 0. That's the safest way to answer it if they didn't give you any more direction on what they wanted. We have a maximum where? Is it 2 or is it 1? Yeah. 1, right? 1/2 is a little bigger than 2/5. That's it. That's the whole question. We did check for undefined, but this function isn't ever undefined. So, right, if we're checking for undefined, so I should say, the derivative is never undefined. Apologies. So is the derivative f prime of x equal to 1 minus x squared over x squared plus 1 squared undefined ever? And the answer is no, because if you look at the denominator, you try and set x squared plus 1 squared equal to 0, there's no real solutions. You'd have to have x squared plus 1 equal to 0, which would mean x squared would have to equal -1, which would lead you to taking the square root of a negative, which is imaginary. So this has no real solutions. So this particular example, well, yeah, so right, so when you're trying to find a critical value, the way we talk about finding critical values is either where the derivative is equal to 0, which we definitely found, right? X could be plus or minus 1, that makes the derivative 0, or where the derivative is undefined. In this case, there aren't any values of that, but we still look for, or at least think about looking for it. The next example will have one though, so let's take a look at that. So let's say we want to again, find absolute extrema of this function f of x equal to x to the 2/5 on the interval from -1 to 32. All right. So we're going to take the derivative, which is 2/5 times x to the -3/5. And if we set this equal to 0, are there any solutions? No. There's nothing that makes this equal 0. If you plug in 0, it's undefined, which is fine. Like we want that point too, but I just want to make it super extra clear that, right, this has no solutions. It might be easier to see if you wrote it as 2 over 5 times x to the +3/5, like that. Then it's a little more obvious that, oh yeah, there's no way this expression can ever actually equal 0, but it can certainly be undefined when x is equal to 0.
Okay, so now we're going to check. We're going to check f of -1, f of 0, and f of 4. Sorry, f of not, that's the, sorry, apologies. Why would I pick 4? That's not right. F of 32, which is going to equal 4, which is 5. So f of -1, -1 to the 2/5 power. Ooh, what is that? Is it 1 or is it -1? Well, you can do either power, you can do it in either order. You can either do -1 squared to the 1/5, or you can do -1 to the 1/5 squared. And either way you do it, you're going to get +1 at the end. -1 squared is 1, and the 5th root of 1 is 1. Or the 5th root of -1 is -1, and the -1 squared is still +1. F of 0 is definitely going to be 0, right? 0 to any positive power is 0. I should, again, emphasize 0 to a negative power is undefined. 0 to a negative power is just like 1 divided by 0 to that positive power. And then f of 32 is going to be 32 to the 2/5 power. Which order should I do these powers in? Should I do 32 squared to the 1/5? Or should I do 32 to the 1/5 squared? Right, I don't know what 32 squared is. And even if I did, I probably wouldn't know what the 5th root of that is. Now, here's the truth is I do know those things, but because I know the other way. I know that 32 to the 1/5 is 2, and 2 squared is 4. This here would be the 5th root of 1024. Which I only know is 4 because I know it the other way. And I only know this is 1024 because it's really 2 to the 10th power, which you should know your powers of 2 up to 10. 2 to the first is 2, squared is 4, 8, 16, 32, 64, 128, 256, 512, 1024. You don't know them, play that dumb game where you would slide the blocks around and the numbers double, right? You'll learn them. I think it's called 2048. That's the next one, right? That's 2 to the 11th. So if you want to know your powers of 2, play that game. It's great. Yeah, f of 0 was defined. F prime of 0 was undefined. So, right, f of 0 is totally cool. F of 0 is just 0 to the 2/5, which is 0 squared, which is 0, and the 5th root of 0 is 0. But f prime of 0 is undefined. Here's what this graph looks like. So this function on this interval from -1 to 32, we got the point -1, 1, got the point 32, 4, and it looks like this. So clearly, an absolute minimum here, an absolute maximum there, right? So we have a maximum at x equals 32 with a value f of 32 equal to 4. We have a minimum, I really should say absolute minimum, absolute maximum, absolute minimum at x equal to 0 with a value of f of 0 equal to 0. But yeah, so what we're seeing here is that, right, this function clearly defined at 0, right? It's definitely continuous, no issues, but it's definitely not differentiable at 0, right? We have a cusp, a pointy point, where it is not, the derivative does not exist there. But that's okay. You can still, right? That's the kind of the very, not the very actually, but that's one of the kind of the interesting things about being a critical point. You can be a critical point where the derivative isn't defined, or the derivative is undefined. You find the critical points using the derivative, but plug it back. Yes. So I should point out, we do this process specifically when we're asked about finding absolute maxima and absolute minima. This is not the process for finding relative extrema. It's a totally different process for that, which I think we might be ready to talk about. Let's see. Do you have any more examples of this? No. Yeah. Oh, yeah. Sure. Mean value theorem. Okay. Well, have you guys talked about the mean value theorem? No. I feel like it's important, but people kind of often skip over it. So let's move along. Yeah. Let's talk about relative extrema. So the idea is we want to find where a function has relative maxima or minima and they're going to occur, they potentially occur at critical points. So the only kind of ways you can have a function having a relative maximum or a relative min, and when I say a relative max or relative min, what I mean is a point on the function that is bigger than everything around it or smaller than everything around it. So graphically, you might say like, there's a relative maximum. It's also a global or absolute maximum, right? Because that's bigger than everything else. Or if I graph something like this, here we have a relative maximum. Here we have a relative minimum. You can say local or you can say relative. They're fairly interchangeable. People do interchange them all the time. I will say them both all the time. Right? Relative meaning I'm bigger than the stuff relative to me, close to me. Local meaning I'm bigger than the stuff that's local to me. So, or local to the point. But you could also have something that look like this, right? If you had a function that say, did this kind of weirdness. Right here, we definitely have a relative maximum. And I'll just point out, the function is definitely not differentiable there. Right? It's pointy. If the function's pointy, it's not differentiable there. Also here, we have a relative minimum, not differentiable there. So whenever we're finding relative extrema, we're looking for critical points because those are the only place where the derivative or where the function could have a relative extrema. And the way we kind of think about this is if the derivative wasn't zero, like if the derivative is positive, it means the function's increasing. So I can't have a relative extrema right there. My derivative is positive, so that can't be the point that's the biggest or the smallest because it's getting bigger to the right and smaller to the left. It can't be either the biggest or the smallest in its local region. Similar thing here, right? If the derivative is negative at this point here, it can't be a relative maximum because the function's bigger to the left. It can't be a relative minimum because the function's smaller to the right. So you can only have possibly a relative max or min where the derivative is either zero or where the derivative is undefined. Because you can have something like this. Oh yeah, the derivative on this side was positive, the derivative on this side was negative. And that actually kind of informs how we talk about what we call the first derivative test. And I'm gonna spell it out very kind of not officially. So here is the first derivative test in a very unofficial way. For a critical value of f of x, call it C. F of x has a maximum, I should say relative maximum, at C if, there's a lot of words I could write here, but what I really want you to see is that what we're going to see, no pun intended there, we have a relative maximum at C if
the function is increasing on the left side of C and decreasing on the right side of C, which we also correlate to the derivative being positive to the left, negative to the right of your critical value. But that makes some amount of sense. If your function is increasing before your critical point and decreasing after your critical point, it had to top out. And then in a similar way, f of x has a relative minimum at C if the opposite behavior. It goes decreasing before C, increasing after C. Now, there's a lot of things I've said without saying anything. The biggest one being that the correlation between a function being increasing or decreasing and its derivative being positive or negative. So we should probably write that down as well. So worth knowing, f of x is increasing is equivalent to the derivative being greater than 0. And f of x being decreasing is equivalent to the derivative being less than 0. There's actually a fair amount of proving of this statement that sometimes people do, and sometimes people just kind of hand wave it away. I don't think it's super important to show you how this is proved. Also, it's fairly tedious and involves the mean value theorem. I'm certainly happy to talk about it next week if you guys really want me to. But you should think about if you actually want to see that, because it's pretty easy to believe. Right? If you look at a function, like if we go back to these pictures over here, right? This function, well, clearly it's increasing here. And if you draw any tangent line is going to have a positive slope. It's definitely decreasing here. And if you draw any tangent line, oh yeah, it's definitely going to have a negative slope, a negative derivative. So I don't think the correlation is hard to believe. If a function is increasing, its derivative is positive. If a function is decreasing, its derivative is negative. Okay. So let's look at an example we've already seen, but in a slightly different light. Let's say we want to talk about this function, but now we're no longer restricting its domain. So we're just looking at f of x equals x cubed minus 6x squared. And I want to know a couple things. I want to know, one, where is this function increasing or decreasing? Let's answer that first. The reason you want to answer this first is, and again, this is looking ahead towards graphing these things. Where the function is increasing, decreasing kind of gives you the most information about the shape of the graph. It's going to really help you draw it, in addition to helping you find where the relative extrema actually are, because you're usually being asked to find those points specifically. But it's really going to actually show you the shape of the thing. So let's find where it's increasing, reducing, meaning I'm going to find where the derivative is positive or negative, which means I'm really going to find where the derivative is equal to 0. Essentially, I want to find the critical points. Actually, I never should say equal to 0 or undefined. I know this one's never going to be undefined, but still, when you're talking critical points, you should always think I'm looking where the derivative is 0 or undefined, because undefined also matters. Okay, so I'm taking my derivative. I already did this before. It's going to be 3x squared minus 12x, which factors is 3x times x minus 4. And we end up getting x equal to 0 and x equal to 4. And then I'm going to put those numbers on the number line in the correct order. And I'm going to think about what my derivative is doing. So I pick a number larger than 4, like 5, and I plug it into my, preferably the factored form of the derivative. And I should point out, I'm now plugging things into the derivative, right? Not the original function, into the derivative. I plug in 5, I get 3 times 5 times 5 minus 4, or really a positive number times a positive number, which means the whole thing is positive over here. So the derivative is positive, which means the function is increasing. And now you can either keep plugging things in. If you plug in 2, you get a positive times a negative. If you plug in -2, you get a negative times a negative. Or you could use the fact that 4 came from this factor with an odd power, and when the power is odd, the sign changes. 0 came from this factor with an odd power, and the power is odd, the sign changes. That's a kind of faster way of doing it if it's comfortable for you. So that means for us that our function is increasing from -infinity to 0, and then decreasing from 0 to 4, and then increasing from 4 to infinity. So here's how you probably need to write this. Again, I will point out some professors differ on how you're actually supposed to write this, but the usually standard way of writing this is that the interval where it's increasing is -infinity to 0, union 4 to infinity, exclusive of the endpoints. Most people define the interval where something is increasing or decreasing as an open interval, where you never include endpoints. But I will say there are some professors who define it as the endpoint being included. So if that's you or your professor, I should say, just be aware of that, that you need to include it if they're saying that. But it's fairly standard to not include endpoints. Decreasing on the interval from 0 to 4. Now, the nice thing about making this sign chart for the derivative and then drawing like the function behavior above it is it's really, really easy to see what kind of relative extremity you might have. This function definitely has a relative maximum at 0 because it's getting bigger and bigger and bigger. It gets as big as it can be, and then it's getting smaller after that. So we definitely have a relative maximum at x equal to 0. And from 0 to 4 and 4 to infinity, before 4, it's getting smaller. After 4, it's getting bigger. So at 4, it had to have been a relative minimum. That's the whole gist of the first derivative test, is that you use this sign chart of the derivative to tell you if you have a relative maximum or a relative minimum. Okay, it's not a lot of time. So let's look at one of my, so let's look at that example. Yeah, that one's, let me think for a second. Yeah, I want that. Okay. Let's look at another example. Let's look at f of x equal to, I don't want to do that. Sorry, I'm trying to make it so it's not too terrible. Yeah, fine, we'll do that one. This example is a little terrible, but it shows you something you need to see. So let's find the critical points. Take my derivative. Okay, product rule, no, sorry, quotient rule. Bottom times the derivative of the top minus the top times the derivative of the bottom, which is 2 times x minus 1 to the first times 1, which I don't need, over x minus 1 squared. This is where you want to be kind of vigilant about your simplification. I don't want to multiply out the whole top if I don't have to. And in fact, here's a good tip. If you're doing the quotient rule and your denominator was already raised to a power, you can definitely factor out some of that from the numerator. Right? Seeing that I have an x minus 1 squared down here, I know I'm going to have x minus 1s in each piece on the top. I can definitely factor out an x minus 1 to the first. That's probably not all, but it's certainly part of it. So let's see, from the top, I can for sure factor out an x minus 1. What else can I factor out from each of these pieces? It looks like a 2 and an x. So let's see, from this first piece, I factored out a 2x times an x minus 1. I'm left with the other x minus 1. From the second piece, I factored out a 2x and an x minus 1. I'm left with just an x. All over x minus 1 to the fourth.
I'm going to cancel an x minus 1 and an x minus 1. And x minus 1 minus x, those x's actually cancel each other out as well. So we're left with just a 2x times negative 1 over x minus 1. Okay, so now we're going to set this equal to 0 / undefined. What's one of my critical values? Or I should say critical values, fine. X equal to what? Let me ask you better. What makes this whole thing equal to 0? 0. Okay, so now I'm going to ask a different question. Well, I'm asking a question. What makes this whole expression undefined? Right. How do I say this without being terrible? X equals 1 is not a critical value. Your answer is still correct. Your answer is very much correct. The question I asked, which is what makes this undefined, your answer is right. In fact, even though x equals 1 isn't actually a critical value, which I'll get to in just a second, it's still important. I still want to think about it. What I usually, gosh, man, I'm so itchy, I'm sorry. What I usually refer to this as is as a pseudo critical value. Why isn't it a critical value? Because it's, oh yeah. Right, it's not in the domain of the original function, right? If you plug in 1 back into the original, it is undefined. What do we actually, if you graph this function, what would you actually have happening at x equal to 1? What kind of nice, maybe not nice, what kind of feature is happening at x equals 1? It's got a vertical asymptote. You definitely can't have a critical point at a place where you don't have a point on the graph. So here's what I want to say about this. X equals 1 is not a critical value, not a critical point, whatever you want to call it. But it's still important. Because if I asked you the question, where is this thing increasing or decreasing, you still want to know about that. Let me show you the wrong answer. If I just included only my real critical values, well, I would look at my derivative, which is negative 2x over x minus 1 cubed. And I'm going to pick something bigger than 0. What do you want to pick? Well, not 1. 1's a terrible choice because if you plug in 1, it's undefined. Let's pick 3. If I pick 3, the top is negative, the bottom's positive, the whole thing's negative. So the mistake I'm making is saying it's all negative over here. Because it's not. Because it's going to change signs or potentially change signs where the derivative is undefined. So even though 1 isn't actually a critical value, it still is a place where the derivative can change signs. And so it's still important to include it on our derivative sign chart. So now if I pick something between 0 and 1, like 1/2, the top is negative. The bottom is also negative because it's a negative number to an odd power. And overall it's positive. And then if I pick something on the other side of 0, like -1, negative 2 times negative 1 is positive. -1 minus 1 is negative. Cubed is still negative. So it's a positive over negative, which is negative. So there's my first derivative. So my first derivative test, my first derivative chart. My function is decreasing, increasing, decreasing. So I would say that I have, let's write the intervals. So it's increasing on the interval from 0 to 1. It's decreasing on the interval from negative infinity to 0, union 1 to infinity. Do I have a relative minimum? Where is my relative minimum? Definitely at x equals 0. Right, because decreasing and then increasing, it definitely bottoms out there. Do I have a relative maximum? No, I don't. So this is where you have to be extra careful, right? If you just look at the sign chart and don't pay too much attention, like, oh yeah, well, it gets bigger than smaller, I have a relative maximum at 1. You can't have a relative maximum at 1. The function's undefined there. So graphically, what's happening is, I can box this over here. And we have a vertical asymptote at 1. We have a relative minimum at 0. And if you plug in 0, the function is equal to 0. So what's happening is probably something like, okay, I know I have a horizontal asymptote of 1, 2, because I've graphed this one before. Also, you guys can see, that, hopefully you all can see that we have a horizontal asymptote at 1, right? Like it's x squared over x squared plus other stuff. And so it probably looks something like this. Well, in fact, I know it's decreasing from negative infinity to 0. So it's doing this kind of deal. And then after 0, it starts increasing from 0 to 1. Then after 1 is decreasing again. I definitely have a relative minimum right there. It also happens to be a global minimum or an absolute minimum, but no one's asking us about that. But I don't have a relative maximum at 1, right? Even though it's increasing and decreasing after, right? At 1, it's undefined. There is no relative maximum there. No, the relative maximum is not infinity. We don't get to say that, right? The function is just undefined. So be really careful, right? You don't get critical, you don't get relative extrema where the function is undefined. But you do have a possible change in behavior, right? Because definitely it's increasing before 1 and decreasing after 1. Okay. There's one other small thing I wanted to say, which is will take me just like a minute. So give me 1 minute if you don't mind. Here's another interesting function. X cubed. You all know what x cubed looks like, I think. What's my only critical point? X is going to be 0. And if I look at the sign chart for the derivative, it is, if I plug in 1, it's positive. If I plug in -1, it's positive. It's increasing, increasing. Two things. No relative extrema. Right, we don't have a relative maximum because it doesn't go increasing, decreasing. We don't have a relative minimum because it doesn't go decreasing, increasing. Now, here's the interesting question to answer. What's the interval it's increasing on? It's negative infinity to infinity. Which I know is kind of, so I want to promise. I want to contrast this with f of x equal to, sorry, brain. Yeah, 1 over x, why not? Which I'm just going to graph for you all. Looks like that, right? Okay. From negative infinity to 0, it's decreasing, right? And from 0 to infinity, it's decreasing. So this is definitely decreasing, negative infinity to 0, union 0 to infinity. And if we take the derivative, right, f prime of x would be -1 over x squared. And here's my sign chart. So the derivative, it's definitely negative, negative. So what's the difference? Why on this one do I not include the 0? And on this one, I do include the 0. Well, it's literally because of how the function is, right? In this function, the function is undefined at 0. Whereas this function, it is defined at 0. And if you think about the graph of this one, that function is increasing everywhere. So I want to say a couple words, then you're free. You're really free to go. So here are the words I want to say. When we think about a function being increasing, we think about it being the same as the derivative being positive. But technically, the definition of a function being increasing is that if you move from left to right, the function got bigger. So really, if you say this function is increasing on some interval, for any 2 points you pick in the interval, the function value on the left should be smaller than the function value on the right. Well, no matter what 2 points you pick for f of x equal to x cubed, 0 being one of them, whatever's on the left is going to have a smaller y value than whatever's on the right, even if one of those choices was 0. So this function is considered to be increasing on the entire interval because even though it happens to have a 0 derivative at the origin, it's only for that one brief moment. And everywhere to the left, it's smaller, and everywhere to the right, it's bigger. So long story short, if a function is increasing, and defined at the point where the derivative was equal to 0, you include it in the interval. Whereas if a function is increasing, and it's undefined at that point, you can't include the